Now we shall have a look at the scope of ESP for the two modes. The considerations are somewhat different for IPv4 and IPv6. We use the packet formats as shown in the figure in the next slide as a starting point. The transport mode ESP is used to encrypt and optionally authenticate the data carried by IP, as shown in the bottom of the next figure shown in the next slide. For this mode using IPv4, the ESP header is inserted into the IP packet immediately prior to the transport layer header. For example, TCP, UDP, ICMP, and an ESP trailer, which comprises of padding, pad length, and next header fields, is placed after the IP packet. If authentication is selected, the ESP authentication data field is added after the ESP trailer. The entire transport level segment plus the ESP trailer are encrypted. Authentication covers all of the ciphertext plus the ESP headers. In the context of IPv6, ESP is viewed as an end-to-end payload. That is, it is not examined or processed by intermediate routers. Therefore, the ESP appears after the IPv6 base header and hop by hop. Routing and fragment extension headers. The destination options extension header could appear before or after the ESP header, depending on the semantics desired. For IPv6, encryption covers the entire transport level segment plus the ESP trailer plus the destination option extension if it occurs after the ESP header. Again, authentication covers the ciphertext plus the ESP header. The transport mode operation may be summarized as: at the source, the block of data consisting of the ESP trailer plus the entire transport layer segment is encrypted, and the plain text of this block is replaced with its ciphertext to form the IP packet for transmission. Authentication is added if this option is selected. The packet is then routed to the destination. Each intermediate router needs to examine and process the IP header plus any plain text IP extension headers but not need to examine the ciphertext. The destination node examines and processes the IP header plus the plaintext IP extension headers. Then, on the basis of SPI, in the SPI header, the destination node decrypts the remainder of the packet to recover the plaintext transport layer segment. The transport mode operation provides confidentiality for any application that uses it, thus avoiding the need to implement confidentiality in every individual application. One drawback to this mode is that it is possible to do traffic analysis on the transmitted packets. The scope of ESP encryption and authentication, as explained in the previous slides, can be visualized as shown in the figure. This can be divided into three groups. First one, indicated by figure A, is before applying ESP. This is how it looks both in IPv4 and IPv6. And as explained in the previous slide, the transport mode operation on IPv4 and IPv6 can be visualized as shown in the figure B. And the figure C shows the tunnel mode operation, which will be explained in the next slide. The tunnel mode ESP. It is used to encrypt an entire IP packet, which is as shown in the bottom part of the previous slide. For this mode, the ESP header is prefixed to the packet and then the packet plus the ESP trailer is encrypted. This method can be used to counter traffic analysis. Because the IP header contains the destination address and possibly source routing directives and hop-by-hop option information, it is not possible simply to transmit the encrypted IP packet prefixed by the ESP header. Intermediate routers would be unable to process such a packet. Therefore, it is necessary to encapsulate the entire block, that is, the ESP header plus ciphertext plus authentication data, if present. With a new IP header that will contain sufficient information for routing but not for the traffic analysis, whereas the transport mode is suitable for protecting connections between hosts that support the ESP feature. The tunnel mode is useful in a configuration that includes a firewall or other sort of security gateway which protects a trusted network from external networks. In this latter case, encryption occurs only between an external host and the security gateway or between two security gateways. This relieves the hosts on the internal network of the processing burden of encryption and simplifies the key distribution task by reducing the number of needed keys. Further, it thwarts the traffic analysis based on ultimate destination. External to internal host protocol operation. Let us consider a case in which an external host wishes to communicate with a host in an internal network, which is protected by a firewall, and in which ESP is implemented in the external host and the firewalls. The following steps will occur for transfer of a transport layer segment from the external host to the internal host. First one, the source prepares an internal IP packet with a destination address of the target internal host. This packet is prefixed by an ESP header. Then the packet and the ESP trailer are encrypted and authentication data may be added. The resulting block is encapsulated with a new IP header whose destination address is the firewall. This forms the outer IP packet. Second one, the outer packet is routed to the destination firewall. Each intermediate router needs to examine and process the outer IP header plus any outer IP extension headers, but does not need to examine the ciphertext. Third one, the destination firewall examines and processes the outer IP header plus any outer IP extension headers. Then, on the basis of the SPI in the ESP header, the destination node decrypts the remainder of the packet to recover the plain text, inner IP packet. This packet is then transmitted in the internal network. The last one, inner packet is routed through 0 or more routers in the internal network to the destination host. Both the modes, as discussed till now, that is the transport and the tunnel mode protocol operation for ESP, can be visualized as shown in the figure here, which is the protocol architecture for both the modes.